like Dr. Eric Sproles to introduce today's speaker. I want to thank you all for coming and also note that the next two rough cuts occur next week and the following week, and they both feature interesting talks on Yellowstone Lake ecosystem dynamics, including those around lake trout. So there's announcements of those on the IOE website, and we look forward to seeing you there. And without further ado, I'll turn it over to Dr. Eric Sproles from the Department of Earth Sciences. Eric, you're muted, but it's good that you are, because I want to remind everyone also that this webinar is being recorded.
There you are. So hello, everyone, and thanks for joining us on a sunny Wednesday. You get extra points for being here on a sunny day in the spring. It's my privilege to introduce Ross Palomaki today. He's going to be our speaker, and he's going to be presenting the first initial stages of his dissertation research. So Ross is in his second year here at Montana State, working on a PhD in earth sciences, and his focus is on river ice, and specifically on the Yellowstone River. And so I'm not going to provide too much content on that, but Ross comes to us from University of Virginia, where he got a master's degree in environmental science with a focus on hydrology. And prior to that, he was a double major at University of North Texas in both mathematics and jazz saxophone. So I look forward to some interpretive saxophone river ice music towards the end of the talk, but that remains to be seen. But with that, I will turn that over to Ross, and remember, please mute your microphone, and if you can, turn off your camera. Thank you so much.
All right, well, thanks, Eric, for the introduction. Let me share my slides here. All right, hopefully everybody can see that. Anybody? Thumbs up?
We got it, Ross.
Excellent, thank you. Great. Well, like I said, thanks, Eric, for the introduction today, and thanks for everybody on the call for joining in to hear my presentation. I'm excited to share some of my dissertation research on river ice. But before I get started today, I'm going to just acknowledge a few folks. In my Geoswirl lab group at Montana State University, thanks to my advisor, Eric, and also my lab mate, Zach, for, among other things, their excellent help out in the field. Thanks to Tanya Franson up at the National Weather Service in Glasgow, Montana, for helping us understand river ice from an operational perspective. And also thanks to Julia Haggerty and Bruce Maxwell as the current and former co-directors on the Montana Institute on Ecosystems. The work that I'll be presenting today received some initial funding both from the Weather Service and the IOE. And so with some of that initial funding, we were able to turn those results into a longer-term grant funded through NASA. So I'm very thankful to the IOE for taking a chance on this project. And yeah, actually, before I jump into this, I need to go mute another computer. I'll be right back. All right, sorry for the delay there. So let's jump right into it. Why do we need to study river ice in the first place? 2 years ago, before I arrived here at MSU, I'm not sure that I could have answered this question myself. My experience with frozen rivers had been pretty limited to very small creeks and streams, and I hadn't really stopped to consider what this problem might look like scaled way up. But it turns out that about a third of Earth's land mass is drained by rivers that seasonally freeze over. And a study from a few years ago estimated $250 million annually in economic costs for North American society to deal with river ice. And wrapped up in that figure is damaged infrastructure, livestock and other agricultural losses, and flood recovery in cities and towns. So even though I hadn't stopped to think about this problem on a larger scale, there are some communities where the pace of life is intricately tied to the presence of seasonal river ice cover. Now, on the scientific side, The study of river ice is fairly new compared to other components of the cryosphere, like glaciers and sea ice. But before it entered the scientific realm, it was approached more from an engineering perspective. So here, this is a picture of a dam on the Manicouagan River. This is part of the hydroelectric infrastructure owned and operated by Hydro-Quebec. And in cold regions like Canada, accumulations of slushy ice both on the river surface and the river bottom can disrupt hydropower generation during critical high demand periods when everybody's trying to warm their homes. On the flip side, frozen rivers provide transportation corridors to some small rural communities up in the Canadian Arctic. And in some cases, these ice roads represent the only way to reach these small villages during the winter months. But potentially the most consequential aspect of river ice on human society is ice jam flooding. An ice jam is a stationary accumulation of ice that restricts water flow in the main river channel. This photo is a bridge over the Danube River in Vienna, Austria, and this was taken back in February 1929. So we've been living alongside river ice for a long time now. As ice flowing downstream encounters some initial blockage, an ice jam can grow tens of kilometers in the upstream direction, and this restricts water flow and can potentially cause backwater flooding. And this backwater flooding can potentially be consequential, but the real threat of ice jams comes during the spring breakup season. If an ice jam releases suddenly, it can send a massive surge of water and ice downstream, which can cause significant and rapid flooding. So let's take a look at an example of this. This is a video clip taken on New Year's Eve of 2014. This is the Gallatin River just south of Big Sky, Montana. And we see in the foreground very low wintertime flows like we would expect. And in the background here, you'll start to see trees losing their snow. And this is because we have this big surge of powerful icy water that's heading downstream toward us very rapidly. So pretty powerful motion here. We can see this took a matter of about 30 seconds to go from low wintertime flow conditions to now all of a sudden the river is overfilled its banks. And on the grand scheme of things, the Gallatin River is really quite a small river. It has an average discharge of about 1,000 cubic feet per second. So let's scale this up even larger. This is the Athabasca River in Alberta, Canada. And this river has an average discharge 20 times larger than the Gallatin River that we just saw. This photo was taken in late April of last year, and an ice jam release during this time caused record flooding in the nearby town of Fort McMurray. As a result of this ice jam release, more than 15,000 people were evacuated from Fort McMurray, and the single flood event caused an estimated $100 million in damages in flood recovery. So there are many rivers around the world that experience river ice and ice jam flooding. And one of the biggest repeat offenders in Montana is the Yellowstone River. So the Yellowstone starts up in the national park. It flows out of Yellowstone Lake and out of Wyoming into Montana here. And then there are about 800 river miles throughout Montana before it hits the border with North Dakota. And shortly after the border is the confluence with the Missouri River. Ice jams historically have formed in many locations along the Yellowstone, but today I'll focus mostly on the eastern part of the state, and specifically the town of Glendive, which today has a population of about 5,000 people. And ice jams have been a problem for residents of Glendive for a long time. This is a photo of the Bell Street Bridge, which is over the Yellowstone right in Glendive. This bridge was built in 1926, but a previous version has existed over this stretch of the river going all the way back to the 1890s. And if you visit the Bell Street Bridge today, you can read on a plaque about an ice jam flood that happened coincidentally on this date, April 7th, back in 1899. So 122 years ago, a huge ice jam released on the river, and it took out the old bridge. It flooded a significant portion of the town of Glendive, and it ended up killing 12 people. The details on the plaque are actually a little bit gruesome, but I'll leave you to read them if you ever go visit. So fast forward a few decades, River ice on the Yellowstone was responsible for one of only 2 bombings of the continental United States during World War II. An ice jam in March 1944 flooded Miles City, which is just upstream of Glendive, and the mayor in Miles City called down to an Army base in Rapid City, South Dakota. And the Army was more than happy to send a couple planes full of bombs to take care of this ice problem. And as you can probably imagine, the bombs were quite effective in breaking up that ice. So water levels receded from the town and the river soon returned to normal. So let's jump ahead another 70 years from March 1944 to March 2014. This is a hydrograph, so we're measuring the water levels over time here. And this is a ice jam event right near Glendive, and we can see that the river levels during this event jumped more than 8 feet in the span of 15 minutes as the result of an ice jam release. This is a photo of the same Bell Street Bridge during this event, and I think this photo really shows how widespread and how powerful an ice jam like this can be. Luckily, the current bridge is sturdier than the one that was built in the 1890s, but an 8-foot surge of water and ice is going to have some far-reaching consequences. During this event, many areas of Glendive again were flooded, including a trailer park near the river that had to be completely evacuated. And additionally, there are some ecological consequences to these events. Many trees along the banks of the Yellowstone River have significant scarring from collisions with massive ice chunks. And it also can be consequential for animals that make their homes near the river. I believe this beaver was photographed also from the Bell Street Bridge during that event. So let's jump forward just one more ice season here. In January 2015, a pipeline carrying crude oil underneath the Yellowstone was damaged and spilled oil into the river and under the ice surface, which you can see in this portion of the photo. It's unclear exactly what caused the buried pipeline to break. It was probably some combination of the big ice event from March 2014 that we just saw and some additional freeze-up effects during the 2015 ice season. But regardless how it happened, trying to take care of an event like this not only puts cleanup workers at risk, having to spend all that time out on the ice, but it turns out trying to recover oil from underneath the ice surface proved to be very inefficient. So the Billings Gazette reported at the end of this event, at least 31,000 gallons of crude oil were spilled into the river, of which less than 10% was recovered by the cleanup crews. There was a long-standing drinking water advisory in the city of Glendive during this period, and oil sheens were detected as far downstream as the Missouri River in North Dakota and as late in the year as April and May of 2015. So hopefully by now I've got you convinced that ice jams and the flooding that they can cause can be very serious. And especially because these flood events can happen very quickly, we would like to have as much advance notice in the days leading up to something like this that we might be experiencing this type of event. But forecasting ice jam floods is challenging for a number of reasons. Currently, in central and eastern Montana, seasonal data collection of river ice mainly consists of visual observations of the river. Oftentimes, these are collected by the roadside. Just drive down the river and write down what you see. And these visual observations are combined with long-term forecasts. So we're looking at 14-day or seasonal temperature outlooks from the Climate Prediction Center, for example. During the breakup season, there's a daily to weekly conference call with county, state, and federal officials from various departments to monitor the progress of ice melt and ice breakup on the Yellowstone. And currently we have no standard quantitative measurements that are being made of this river ice. And I want to be clear here that this is not a criticism of the current system. Many of the counties that have to deal with river ice on the Yellowstone have very low population densities, and they have very few resources to devote to river ice monitoring. Additionally, collecting this type of quantitative observation of river ice is not exactly a walk in the park. Here we see some very brave researchers out of Finland drilling boreholes in the ice on the left, and on the right, dragging ground-penetrating radar along a transect of the frozen river. Traditional measurement techniques like this require a lot of time and a lot of special training, which costs additional money. And honestly, it's a little bit unnerving to think about spending that much time out on the ice surface. But without quantitative measurements like this, we can't answer questions like how much ice was present when a given flood event occurred. Does the ice extent always correlate with ice volume? How do the extent or the volume of river ice correlate with ice jam flooding? And we could continue with many more questions here relating to timing and ice jam formation and breakup and everything. But the point here is that we would really like to have some numbers available so that we can start answering questions like this. So that's where my research comes into play. For this project, we are ultimately working toward the goal of improving ice jam flood forecasts on the Yellowstone River. In order to forecast for ice jams, we first need to quantify river ice at a regional scale. If we're able to do that, we can generate a flood forecast using current ice conditions and projected meteorological and hydrological variables. So in order to quantify river ice, we train a neural network to detect it within satellite imagery, and then we validate our satellite-based estimates with UAV measurements that we make from the ground. So these two aspects of the project together represent the first widespread comparison of river ice between ground-based and space-based remote sensing platforms. In the time it takes to drill a few boreholes by going out onto the ice, we can collect UAV measurements that turn into thousands of measurements of depth or volume that provide a picture of the spatial variability of ice over a small section of the river that we're investigating. To our knowledge, this is also the first time that a neural network has been used for automated detection of river ice in satellite imagery. So for the remainder of the presentation, I'm going to talk in a little bit more detail about these two aspects of the project, and we'll get started first with a little bit more background information about satellite imagery. So what we have in mind for the end result of this project is an operational tool that would take new satellite imagery, identify all of the river ice in that image, and then derive quantitative properties of the ice that can provide useful information to flood forecasters. And we know from previous studies that river ice can indeed be detected in satellite images. This is a figure from a paper published last year in Nature. And in this one, the authors used the historical record of Landsat visible imagery going all the way back to 1984. And they were examining spatial and temporal changes of river ice cover that have occurred in the past 3 decades or so. The authors extended their findings from the satellite record with climate projections in order to consider future potential river ice scenarios. And visible imagery was a perfect tool for this type of long-term historical analysis. But when we think about our operational product, with visible imagery, you can easily go from an image like this, taken on a nice clear day, to something like this if the clouds roll in on the next day. And if this happens during a critical forecasting period, as the breakup season is setting in, all of a sudden our operational tool is really providing no information to the flood forecasters. Additionally, as I mentioned, we're hoping to derive quantitative properties of the ice like thickness and volume, and we can't do that using just visible imagery alone. So luckily for us, there are many other satellites in orbit collecting other data that we have access to. So very broadly, we can separate Earth-observing satellites into 2 categories. The first category is called passive remote sensing. This is like the Landsat imagery that we just saw. Passive remote sensors detect and measure naturally occurring radiation. So in this diagram here, electromagnetic radiation emitted by the sun gets reflected off of something that's on or near the Earth's surface, and then that reflected radiation is measured by the sensors on our satellite. And we're not just talking about visible light here. If we again consider the Landsat 8 platform, it measures radiation in 11 different bands, and bands is just a remote sensing term that refers to the range of wavelengths detected by a given sensor. So on the Landsat 8 platform, bands 1 through 4 do fall into the visible spectrum, but bands 5 and onwards are sections of the electromagnetic spectrum that fall outside what we're able to detect with our eyes. Now, the second category of remote sensors is called active remote sensing. This is where the sensor provides its own source of energy. So active remote sensors emit radiation directed towards some target and then measure how much of that radiation reflects off of the target and then is returned back to the sensor. We can employ active remote sensors in different ways depending on the wavelength of the radiation that they emit. So one particular technology that's very interesting to us for this project is called synthetic aperture radar, or SAR. And SAR remote sensors emit radiation with wavelengths around the 5 centimeter range. This is 5 orders of magnitude larger than the wavelengths of visible light. And wavelengths this large are not affected by clouds. The radiation passes right through them without significant reflection. So in a sense, it allows us to see through those clouds. And they also work day or night and don't depend on light from the sun in order to collect data. So this is a big bonus for collecting river ice imagery in high latitudes where the areas on Earth don't receive much sunlight during the winter. So SAR imagery is a great tool for river ice detection. And certainly we are not the first people to have this idea. In this example from 2015, the authors used SAR data collected by the RadarSat-2 satellite, and they investigated ice on the Slave River in Alberta, Canada. In these figures here, the river flows into the frame from the bottom, and then it flows north and west, ultimately into the Great Slave Lake. And so in these panels, we're looking at an area of about 50 by 50 kilometers. So these maps show SAR images collected on 2 different dates during the 2014 and 2015 ice season. The authors used the imagery to separate ice-covered river sections from open water sections, and then they further divided the ice cover into 3 primary ice types, which you can see the different colors highlighted on the river. This is important information for river forecasters because different ice types have different implications for potential ice jams. So to understand how this is possible, let's take a look at some of the processes that drive river ice formation. In a very general sense here, we can expect the development of river ice over the course of a typical winter to look something like this. The terms on this slide come from the book River Ice Formation, which was published in 2013 by the Canadian Geophysical Union. And I'll show some examples of these different ice types in the coming slides, and the figures I'll use are also taken from that same book. So at the beginning of the freeze-up period, there are 2 processes that begin at about the same time. One process results in border ice, and the other forms something called frazzle ice, which eventually produces pancake ice. Given enough time and enough cold weather, border ice and pancake ice can form 2 different types of ice covers in the midwinter period. These are called juxtaposed and consolidated ice covers, and they can persist for a number of weeks to months. Under certain conditions, an ice feature called a hanging dam may develop, which persists into the breakup period. And then finally, the season-long history of ice development combines with the meteorological and hydraulic conditions during the spring breakup season to potentially form ice jams. And let me reiterate here that this is a very general picture, and there are many exceptions of this to this timeline. So, for example, the video clip I showed you at the beginning was taken on New Year's Eve at the Gallatin River, and we would consider that generally to be somewhere at the end of this freeze-up period. So an early season cold snap followed by a sudden warming event can potentially condense this season-long timeline here into the span of about a week. So let me show you some examples of these ice types, and then we'll consider how we can distinguish them in a SAR satellite image. So as summer transitions into the autumn season and days become shorter and colder, ice begins to form in the shallow and slow-moving waters right near the riverbank. This border ice growth generally begins as a thermal process. So heat exchange between the shallow water and the cold air right above it becomes negative, and as we have heat moving from the water into the atmosphere, the water freezes into ice. And this begins somewhat of a feedback process. the border ice grows laterally inwards toward the center of the channel and at the same time downward in thickness. This growth affects the hydraulics of the channel because as the ice grows further and further out, it slows down flow in different areas of the channel, which promotes additional ice formation. So I think this is pretty clear in these photos. On the left here, we have a localized region of low stream flow velocities that exist behind this island. And you can differentiate older ice that has snow on top of it from newer ice growth, which does not yet have any snow cover. So at the same time that border ice is growing, there's another process of river ice formation happening simultaneously that results in frazzle ice. And from the river ice formation book, there's a sentence in there that says, frazzle ice exists anywhere where turbulence and supercooled water exist together. So for this diagram, imagine a river on a cold, clear night. Thanks to heat loss from the river into the atmosphere, we have a very thin layer of supercooled water on the surface of the flow. So this is liquid water that has a temperature below freezing. And in a region of rapids, for example, turbulent flow results in increased transfer of water vapor from the river again into the atmosphere. And if the air right above the water surface is cold enough, this water vapor can very quickly condense into an ice crystal and fall back into the water. And remember that the top layer of this is supercooled water. It's water below freezing. So it only takes a few initial ice crystals, which in this diagram are called seed crystals, to enter the water and set off a chain reaction in that supercooled water to form many new ice crystals very, very quickly. And these ice crystals are called frazzle ice. So the fate of our newly formed frazzle ice depends on the hydraulic environment. Some of the frazzle adheres to the substrate on the bottom of the river in something called anchor ice. But most of it floats freely around in the water column and collides with neighboring ice crystals and eventually forms larger and larger pieces. These are called flocks in this diagram. And as we continue to float downstream, more collisions are happening, more ice crystals are adhering together, and as these pieces grow larger and larger, eventually they become buoyant and float to the surface. So just to summarize this diagram, we start with many, many small crystals here. As they move downstream, they're colliding with each other, adhering to each other, growing larger, and eventually floating to the surface. And once they do arrive at the surface, these large cohesive pieces of ice are called pancake ice. They get their characteristic round shape, as I mentioned, from repeated collisions under the surface, but also on the surface with other ice pieces as they continue to travel downstream. If cold temperatures persist, the exposed portion of this pancake gradually turns into a solid ice cover, while additional frazzle slush collects underneath it under the water surface. And I think that this is a really cool photo here and a really interesting phenomenon to see in person. But let's also not forget about the border ice that we saw just a few slides ago. So as pancake ice moves downstream and encounters a narrower part of the channel, potentially due to encroaching border ice growth from the riverbanks, it can begin to back up and form what is called a juxtaposed ice cover. What happens next depends again on the hydraulic environment and the meteorological conditions. So here's a diagram of a piece of pancake ice that has encountered a stationary ice cover. Initially, we have balanced forces in the upward and downward direction, and so our pancake remains on the surface. As more and more pancake ice reaches this point in the river, we start to get a traffic jam. In pretty rare circumstances, this ice could freeze in this formation, and we would have a very widespread but thin ice cover that does not extend very far down vertically into the water column. But this is a very complex and a constantly evolving hydraulic environment here. So each new piece of ice that enters the traffic jam very slightly changes the flow, which subtly changes the forces acting upon all these ice pieces. So what typically happens in a chaotic system like this is the collapse of our widespread and thin ice cover into something much more compact called consolidated ice, which occupies a much larger portion of the vertical water column. And it's very likely that we still have a lot of free-floating frazzle ice in this portion of the water column, which now all of a sudden has a much larger target where it can be deposited. Accumulations of frazzle ice on the underside of a consolidated ice cover like this are called hanging dams. So here's a photo that shows the structure of a hanging dam. We have a thin layer of snow cover on top of a thicker layer of very solid ice, and then below that, an even thicker layer of now frozen frazzle slush. So hanging dams can grow to be many kilometers long across the river and in the downstream direction as well, and can severely restrict flow in the channel depending on the amount of vertical space that they take up in the water column. This sets us up for backwater flooding in the near term and the potential for sudden ice jam release and flooding in the long term. And because we have so many formation processes happening at the same time, many of which are sensitive to hydroclimatic conditions, river ice formation is very dynamic and it's highly variable over space and time. It's very likely that we would have different types of ice existing simultaneously on the same river, but different reaches of that river. So the spatial and temporal evolution of this ice cover is very important information for a flood forecaster. If we return to this figure, time series satellite images like this can help river forecasters understand the history of ice over the course of a season. We can examine specific locations along a river and look for changes in ice conditions, which may give us an indication of how the ice may continue to evolve moving forward. So the authors of this study were able to create these classification maps because different types of ice surfaces, like we just looked at, reflect SAR radiation in different patterns. So I'll show you what I mean here. A smooth ice cover, like something we would expect from border ice growth, provides a mirror-like surface for the radiation to reflect off of. Most of this reflected radiation, which is also called backscatter, travels in one primary direction. And on the other hand, a rough ice surface scatters the incoming radiation in many directions, and typically we would have more radiation return to the sensor from a rough ice surface than from a smooth ice surface. So it's these quantitative differences in backscatter that were leveraged to ultimately create the river ice maps from the previous figure. And there have also been some studies that indicate a correlation between the thickness of ice and the pattern of radiation backscatter that our satellite measures. And we'll explore this in a little bit more detail later, but for now, this is great news for us. Because if we can reliably and accurately classify river ice pixels within a satellite image, we can then use SAR backscatter data to determine the quantitative properties of that ice that will eventually help flood forecasters. So this is where the neural network comes into this research. We use a neural network to classify our satellite image and automatically pick out the river ice. So let's take a look at how that works in a little bit more detail. In remote sensing studies that combine neural networks with satellite imagery, there are a few different types of tasks that we can ask our neural network to perform for us. The one that we use for this research is called image segmentation. This is a pixel level classifier based on predetermined categories that we choose. So we give a satellite image as input data, and the neural network gives us a map where every single pixel of that satellite image is classified into some categories that we have determined are useful for our project. The idea here is that instead of me looking at a satellite image and spending hours clicking on every single pixel that I think is river ice, we can train a neural network to do it automatically, and eventually we get our results back in a matter of seconds. So to understand the principles of our neural network, I want to share two important bits of background information with you. One about digital images, and then another about an image processing technique called a convolution. So for now, let's step back from our satellite image, and we'll consider a much simpler and also a much cuter image of a puppy. So this puppy, just like all digital images, is made of small building blocks called pixels. And we can zoom in onto an individual pixel here and see that it's made up of a uniform color. And most of our computer displays and many pieces of software that we use today represent this color with an RGB triplet. So this is an additive color model where red, green, and blue colors, each with a certain intensity, are added together to get our light brown color. And combinations of red, green, and blue in different intensities result in the different colors of the pixels that we see throughout our digital image. So another way that we could think about our puppy image here is that instead of one image, it's actually 3 images stacked on top of each other, where one image contains the information about how red the pixels are, one contains the green information, and one contains the blue. And this is essentially how we construct images a lot of times in the remote sensing world. We have one image made of multiple bands, and we already saw how one satellite can have multiple sensors to capture the intensity of red, green, and blue light that's reflected off of the Earth's surface. So we can zoom into just one of these bands here. Let's take a look at our blue band. And we can represent the blueness of each pixel just with the appropriate number. So on the right, this is the numerical information that comprises one of 3 bands of our original puppy image, and specifically how blue each of those pixels are. So in some slides coming up, I'm going to use the term matrix. And I'm sorry to all of you Keanu Reeves fans out there, I'm not talking about the movie today, but I'm going to use this term to refer to a collection of numbers organized in rows and columns like we see here on the right-hand side. So digital images, the 2 things I hope that you can remember. Number 1, they're made up of pixels, and those pixels hold numerical values. And number 2, that one image can be comprised of multiple bands. So let's move on to the second bit of information, something called a convolution. So in mathematics, a convolution is a specific operation that combines 2 functions to produce a third function. But in image processing, instead of functions, we're going to combine 2 matrices to produce a third matrix. So let's look at an example here where our first matrix, our input image, is just the blue band of our puppy. So we're looking at blue pixels here, but we know that under the hood, we can also represent these just with numbers. Our second matrix is called a convolutional kernel. Just like our input image, we've got a grid of numerical values. And for now, the actual numbers here don't matter to us very much, so we'll just stick with question marks. And to generate our third image, our resulting image, or matrix, we take our convolutional kernel and very systematically and methodically traverse along the rows of our input image, one small portion at a time. So here I've got a 3x3 kernel, and I'm going to start in the upper left-hand corner of my input image with a small 3x3 subsection. And we're going to use those values to get a single pixel in our resulting matrix. And as we just continue to move across the input image, we can calculate different pixels in our result. So, and it's important to note here, we're using a total of 9 pixels in our input image, combined with the 9 pixels of the kernel to just produce a single pixel value in the resulting matrix. So if this seems a little bit confusing, let's take a look at it in an animated form here. So here we can see our gray convolution kernel traversing across our blue input image. And I think this animated form is easier to see how the 9 kernels of the input image are used to calculate just a single pixel of our resulting image up in teal. So how exactly do we calculate the result from the input image and the kernel? It turns out it's a linear algebra operation called a dot product. And right now, I can't see many of your faces on this Zoom call, but I know for sure that there were at least a few of you who just cringed at that thought of linear algebra. But I promise you, it's really not so bad. So let's take a look at an example here with some actual numbers. So now we've got some numbers assigned to the pixel in our input image, as well as the pixels in our kernel. And again, let's start in the upper left-hand corner. All we're doing is aligning pairs of numbers between the input image and the kernel. We're multiplying those pairs of numbers together, and then we add everything up. And the final number is the value that we put into the pixel of our resulting image. And if we continue our systematic traverse along our input image, we can fill in the rest of our pixel values. So I know that you don't want to talk all day about dot products and matrix math, but why am I telling you about convolutions in general? Why are they important for this research in particular? It turns out that depending on what numbers you have in your convolutional kernel, you can alter your input image in different ways to produce different visual effects. So let's take a look at that with a concrete example here. We'll start with a pretty simple kernel. I'm essentially just taking an average of 9 pixels in my original image, and the result is we slightly blur our image in the result. So we can change these numbers up a little bit. And now with these with this type of convolutional kernel, the result is that all of the horizontal lines in our original image are highlighted and everything else kind of fades into the background. Let's change it one more time. Now with this kernel, we're detecting all of the horizontal and vertical lines at the same time. And this is something called edge detection. We can see all of the edges are now highlighted in our image. And we could continue here with many different examples of many other kernels, but what I want you to know is that different convolutional kernels detect different features in any input image. So this brings us to the fundamental idea behind our convolutional neural network. Essentially, we take many satellite images of river ice and we create answer keys for them by hand. So I go in and say, this pixel is river ice. This pixel is open water. This pixel is an agricultural field, whatever we want to use. The idea is that there are one or more features of the river ice pixels that very clearly differentiate them from all of the other categories. The thing is, it's difficult for us as humans to explicitly determine what those features are. It's not as easy anymore as just going in and highlighting all the lines on a building. So instead, we feed all of these satellite images into a neural network as training data. And the neural network uses a long chain of convolutions on top of other convolutions to try to figure out what those features are that separate the river ice pixels from all of the other pixels. And if we've done a good job creating this training data set, and we've done a good job building an appropriate network architecture, our trained model can take a new, never before seen satellite image and accurately classify all the pixels based on the categories that we picked out. So for this talk today, I'm not going to get into too much detail about what's happening under the hood or inside this black box of a neural network, but I'll admit that there's a lot of complexity going on in there, but it's important that we take a step back sometimes and remember that at the end of the day, our neural network is just another computer algorithm that's producing some sort of output using some sort of input. And in that sense, it doesn't matter if we're using a neural network or a physically based model or a statistical model or whatever you want to use. We will never be able to produce quality output with a model if we don't have access to quality input data. To put this more succinctly, garbage in equals garbage out. So we need to put a lot of thoughtful consideration into our training data. We can ask questions like, how much training data do we need? We might think, hey, the more the better. Let's use 10,000 satellite images. But that means I have to hand create 10,000 answer keys for all those images, which is going to take me a very long time. Which locations should we use of Earth? We know that we're trying to forecast for the Yellowstone River, but maybe if we bring in ice from the Athabasca River or from the Gallatin River, that might help us generalize some of these ice types. Maybe the most important questions that we need to ask are which satellites are we going to use and which bands from those satellites are we going to get our data from? So ultimately for this project, we're taking a first attempt using SAR imagery from the Sentinel-1 satellite and visible imagery from Sentinel-2 to form an input image that has 5 or more bands. The combination of visible and SAR imagery together provides more information to our network than using either type of image by itself. And also, because we include the SAR imagery, that allows us to derive the quantitative properties that we're looking for. So we put all these together and throw it through our neural network, and what do we get? Well, this is the point in the talk where I wish I could say, boom, look, we have 97% accuracy with our river ice classification. we're doing an excellent job here. But in reality, I am still very much in the process of getting our neural network up and running. And thankfully for me, I've got another 2 years of this PhD program to get everything worked out. So for now, let's just everyone cross our fingers and send me some good vibes that eventually we'll be able to achieve high classification accuracy using this process. But for now, let's go back to something that I've been saying a lot today about including SAR data to derive quantitative properties of the river ice that we can see in the images. How do we validate those type of numbers? We've already ruled out at the beginning of the presentation that we don't want to go step out onto the ice and drill boreholes. So we need to figure out some other way to measure the thickness of the ice on the ground to validate our satellite measurements. So for this project, we used a technique called structure from motion photogrammetry. This video clip was taken in February of this year out in Glendive. You can actually see the Bell Street Bridge up in the top left-hand corner. And thanks to Zach Miller for this spectacular videography work. So instead of walking out over the ice, instead we remain safely on the riverbanks and we fly a drone out over the frozen river. Our drone is equipped with a high-resolution RGB camera, so just a regular camera like you might use to photograph a landscape. And we create flight plans in a lawnmower pattern over the river. And then the drone takes hundreds of overlapping images as it follows the pre-established flight path. And then each time the camera takes a photo, location and camera angle information are attached to that image, and those images are represented here by the blue squares. The drone that we use for this project is connected to a real-time kinematics base station, which is a GPS system that tracks the position of the drone in the air to centimeter scale accuracy. And since all of the photos that we're taking are gradually overlapping, any given feature in the scene below is visible in multiple photos. So that means that every piece of ice that we photograph on the river is seen from multiple viewing angles. And then the structure from motion photogrammetry, the structure from motion algorithm uses trigonometry to combine these multiple viewing angles with the precise drone locations to create a model of the larger surface underneath using the individual photos. And in addition to the precise onboard GPS system, we also collect a number of ground control points using mobile GPS units. The structure from motion algorithm uses these known reference points as a way to further improve the geolocation accuracy of our models. So what do these models look like? Let's take a look. This is an orthophoto stitched together from hundreds of individual images of the Yellowstone River near Glendive. I don't have a scale bar for you on this image, but you can get a sense of the relative scale by looking at these two cars near the right edge of the shot. So the river channel here is about 2 football fields wide, give or take. So this is an orthophoto. Let's have a look at some models here. On the left, we have the digital surface model, and on the right, a digital elevation model that we're generating using that same photo set. The results here show that our drone can very easily resolve differences in both surface roughness and surface height across the river channel. So to derive an ice thickness measurement or an ice volume measurement from something like this, we need to generate a second elevation model at the same location in the river, but we'll take it this time in ice-free conditions. We can subtract the ice-on model from the ice-free model, and then after we account for differences in the water levels on those 2 different days, we attribute the remaining change to the presence of ice on the river. So currently, this is what our ice-free model looks like. This is the same river location just south of the Bell Street Bridge. And we can see a nice smooth surface here, kind of in the lower part of the channel. But on this day, it was a beautiful day for flying, really nice and sunny. But unfortunately, we had some very bright reflections off the water in this part of the image, which are causing some jagged artifacts to be present in the model. So we're still working through that. We also just wrapped up our first big field collection season last month. So I'm still processing the many thousands of photos that we took over the season into various digital models at different timestamps. So hopefully we'll be able to get some initial numbers of those pretty soon. So I'm going to wrap up today just by describing kind of where this research is going over the next 2 years and beyond. As I mentioned, I have plenty of photos to process from this past field season, and we'll get our digital elevation models going and be able to derive our first ice thickness and volume measurements from the ground. Once I have those up and running, we'll be able to start our comparisons between those ground-based digital models and the SAR backscatter imagery and start to develop some sort of correlation there. As I mentioned, certainly plenty more work to do in this neural network training process. We're continuing to work through that. And then looking even further down the road, we're hoping that ultimately this framework will lay the foundation to incorporate SAR data from 2 upcoming NASA satellite missions. The first is the SWAT mission, which is scheduled for launch in April 2022. And this will provide SAR measurements targeted at the Earth's freshwater bodies. This includes surface water heights for many rivers, including the Yellowstone. This could improve the accuracy of our ice thickness estimates by more accurately accounting for differences in river stage or water levels on a regional scale. And then on the right, we have the Nysar mission. This is scheduled for launch in September of 2022. And this will provide SAR measurements down to a spatial resolution of 3 meters. This is much higher than anything we have access to now. And this could enable us to resolve different ice types at much finer scales on rivers across the globe. So with that, I will stop for now. Thank you very much for listening today, for tuning in, and I will be happy to take any questions that you have.
Hi there, everyone. You can, there we are. So I'm going to be leading moderating the Q&A. And so just a quick address to Tracy Sears. Yes, this presentation was recorded, and I believe Paige will be able to provide the link on the Institute on Ecosystems website. Just as you can tell, Ross was funded by a 3-year NASA finance proposal for his dissertation research, and you can see why this is why they were so interested. And also for everyone out there, want to really thank Tanya Franson, who's also on this call from National Weather Service. And this project kind of came out of ideas with her when she did an IOE presentation as well. So take these nuggets of information from a seminar and generate ideas from them. With that, I'll open it up for questions for Ross, and you can either type them in the chat or just ask him, turn on your mic and ask the questions. We'll do, Ross. I will start to get things started.
Sure.
How are you running from a technical standpoint? Are you using standard remote sensing software, or are you using something more specialized?
Yeah, so we have access these days to pretty sophisticated like data pipelines, I suppose. I get all of my satellite imagery that I use from something called Google Earth Engine. It's essentially Google's cloud-based GIS software that has a really extensive satellite data catalog. And it's all run on cloud servers somewhere. So I really don't have to do much data downloading, initial image processing, anything like that. So I'm able to access a ton of images through there. And then I bring everything into typically like a Python notebook or some sort of other open source coding notebook. And those are great because I also can run the neural network computing and the training process. Everything that's really heavy on the computer, I can also run in a cloud-based environment. So very little of what I have to do, I actually don't need to do much of it on my own machine at all, which is pretty nice.
Great. So we have a question from Andrew Leskowski. And what are the main challenges in linking drone data with satellite data with regards to neural network training?
Yeah, that's a great question. Thanks, Andrew, for asking that one. I think that the main thing that we're going to run into is there's a lot of post-processing happening behind the scenes, just to make sure that our drone models are spatially accurate and geolocated in the appropriate place. Because we're dealing with these models that are much finer scale than the satellite pixels that we have. So our models are around the 5 centimeter per pixel resolution, whereas the Sentinel-1 SAR images are a 10-meter resolution. So there's a lot of kind of processing happening when you move between such different spatial scales like that. But the first thing that we have to do is make sure that we can remove as much location error in our drone models that we possibly can. So there's a lot of work that I'll need to do coming up to ensure that I've got highly accurate spatial models. And then we'll get into the process of addressing that difference in scale.
Ross,
Great.
awesome presentation. Really nice.
Thanks, Zach.
You mentioned that RADARSat-2 paper. Did they look into how much of that backscatter is coming volumetrically within the ice? How much is coming from the air-ice interface? How deep this C-band is penetrating into ice? Things like that. Is that something that you have a clear idea about?
Yeah, that's a really good question. The folks up in who work for the Canadian Geophysical Union have been doing ice studies for a long time, and I believe that they have done mostly laboratory experiments of how deep that C-band penetrates into various ice types. So they do have at least some initial lab results on that. In that paper in particular, the way that they classified the different ice types was through a K-means classification. So I don't believe that in that classification they went in and broke out the different components of the different interfaces, for example. But there is some work done on that from the lab setting to sort of get at something like that, at those decompositions.
Awesome. Thanks, man.
Mm-hmm.
Any other questions? I know we have some folks from the operational side of things. Any questions from the less research and more operational perspective?
I have another question.
Go for it, Zach.
You said you're going to incorporate Sentinel-2. Won't that introduce the exact same visible cloud cover night issues that you were trying to avoid by using Sentinel-1 SAR imagery? Are you going to work with both inputs and see if you could eliminate it at some point?
Yeah, so what I'm kind of hoping is that we can get some overlapping images where I essentially envision it as a comparison between multiple neural networks, where if I can get the input data for training, I'll have some where it's the visible and the SAR imagery stacked together. I assume that that additional information between the two satellites will ultimately provide the best classification accuracy. But just like you mentioned, we can't rely on having a visible image for this operational product. So instead, I'd like to compare the visible plus SAR imagery to a neural network trained only with SAR imagery, and have a comparison there between the accuracy of the classification. But ultimately, I expect that that would be more useful in an operational setting.
I think that makes a ton of sense. That'd be cool to see.
Yeah.
Will do. Well, we are at the top of the hour, so I'll open it up one last time for questions, and if not, we will move on to our next step. Oh, we have something. Here we are. So from Sean Carter at the National Water Center in Tuscaloosa. As someone who does river ice classifications with SAR imagery operationally, what kind of controls are you using to control your EO, and SAR sandwiches, as there can be significant change in ice structure from one day to the next?
Yeah, so an excellent point, and something that we're still working through, essentially, because yeah, potentially these images are taken a few days apart, where the ice could move substantially in those few days. So, Sean, that's a great question, and something that we're still working through.